operating system. This is a canned thing I use all the time. Okay, yeah. If you take a course on operating systems, you ought to at least know what an operating system is, right? Abstraction layer. It sits on top of the resources and manages those resources. Okay, and that goes all the way back to just about every paper that we talked about. It mentioned in some form or another those two repeating concepts. Okay, something that insulates you from the hardware. Okay, and manages the hardware under the covers for you so that you don't have to do it as a programmer. All right, so that everyone did pretty well on that one. Okay, the next question. So the way I answered this is so I'll just start with the primitive column. The first two were primitive and the rest were considered modern. All right, then fixed or extensible. The first four went fixed, extensible, fixed, extensible. Then I considered both Multics and Unix to be fixed. Okay, one typically doesn't take Unix and add to its operating system capability at the end user stage. Right? One installs Unix and uses it. Okay, unlike, for example, the nucleus. And remember, by definition, you took the nucleus with a bare minimum set of capabilities and you extended it to be what you wanted it to be. Similarly with Hydra, okay? You took the Hydra and you glued on the stuff that you wanted to make it be what you wanted it to be. The others, the 10x, Multics, and Unix, basically, once it got installed, that was it, okay? Could you extend Unix? Sure. I could grab the Linux kernel and glue a bunch of stuff on if I wanted. But in general, that's not what happens. Most people, when they install Unix, they get a binary, okay? They stick the CD in their machine, and it gets installed. That's the end of it. They're not about extending. So that was my view on fixed or extensible. And then in the last column, it went production, experimental, and the last two were production. And so I called Nucleus an experimental system because they were using it to do operating system experiments or computer science-like experiments, similarly with Hydra. Okay? Whereas the 10x, Multics, and Unix, once the operating system was in place so you could do other work. Okay, you could do other work. It wasn't designed to do computer engineering or computer software engineering, computer engineering, or computer science research. It was to do something else, to run codes. So that was the way I broke that down. Question number 3. This deals with process. So what's a process? Well, it's a program or a piece of code in execution. Okay? And we already saw that the process table is either an array or linked list. There's one entry for each process. How do you identify that process? What's the thing? Yeah, PID, the process ID. How can you get a process ID in Unix? How about PS? If you invoke at the command line, PS, it'll show you all the processes and their PIDs. Okay? All right? And then there's a whole boatload of switches associated with PS. How can I find out what those are? Man, space, PS. And there's PS-A, PS-AE, PS-.
I tried that on my Ubuntu, on that Linux, and
yes.
I couldn't get nothing to pull up under me.
Ubuntu may not have the man pages installed. So man pages are extra documentation, and depending on what Ubuntu you got, it may have been a bare bones Ubuntu that goes on an 80 meg disk. So Ubuntu's target is low-end, very small systems. Okay, and that's a good place, by the way. I'm not knocking it, but man pages take up oodles of space, so it may not have Ubuntu.
I pulled up the iNodes and everything.
Yes. So the man pages may not be installed. There's probably some mechanism by which you can add the man pages, but they'll be on the FLAC for sure. They'll be on your Flacintosh for sure. The man pages, okay? So process table. The third one, no, a process table doesn't start with an inode. Okay, that was pure deception on my part.
Oh, that wasn't right.
I know. And you know what? I feel terrible.
Right.
Okay, a process table doesn't start with an inode. All right? It's a file that starts with an inode, not a process. Okay? A file starts with an inode, and it contains the metadata and the addresses of blocks. Okay? So this was a complete charade, a red herring. You've heard that English terminology, red herring? No. That means nonsense, or it's sometimes called a white elephant. A white elephant or a red herring is something that's ridiculous. It doesn't really exist. I'm sure that in your language there's a similar terminology.
When we say white elephant, we mean something corrupt.
Yeah, no. In our, and for us it's something that's nonsense. Like, bill of goods. They sold them a bill of goods. It's nothing. It's nonsense. Or a pig and a poke. Okay. So a pig and a poke comes from medieval times where people would sell them a cat and bear. Okay. That's also where the term cat's out of the bag comes from. So a pig and a poke, you have to be very careful what you were buying. So red herring, so that was a red herring. Number 4, true. On a uniprocessor, multi-programming creates the illusion that the processes are simultaneously running. And how does it create that illusion?
We're excited. Use a quantum time to every process.
Yes. Those are the words I was looking for. It gives a quantum of time to each process. It runs it for a while, then it puts another process, and it puts another process. So question, what do you suppose happens to the quantum as the number of processes increases? Yeah, the quantum gets smaller and smaller and smaller. Now, when you change from one process to another, that's called a context switch. That's if you want to use a 50-cent phrase and impress your friends, yeah, my computer's undergoing a context switch. Right? Yeah, you want to use highfalutin lingo. So anyway, a process switch, context switch rather, takes time because it has to save all the state of the executing process somewhere, okay? Then it has to bring in the new process, restore all its state, right? Blah, blah, blah. So all that takes time. So what can happen is if the quantum becomes so short that the context switch time becomes a significant piece of the quantum, then you get a terminology a condition that's known as thrashing. Thrashing. That's where it spends all the time process switching and no work gets done. It can happen to humans at work. Okay, your boss gives you so much crap to do. Okay, so by the time you remember the new one, oh, okay. Can I get an amen? Amen. Amen means I agree with that. Okay, I agree with that.
We all have that word.
Yeah. In our churches, if a preacher says something that you agree with, everybody goes, amen.
We say amen.
Okay, it's the same thing. I agree with that. That's good stuff. It's not a red herring.
It's pretty much like made it happen.
Yes. Okay, sure. Okay, so next one. Also true. Process table entries usually fall in one of 3 categories. Either the process management itself, the memory management, or the file management. There may be some other ancillary pieces, some miscellaneous stuff, but largely these are the 3 major categories in which the process table entries can be broken. Okay? The next one, also true. Threads are sometimes known as lightweight processes. The next one is false. Thread scheduling does not have to be handled by the OS. An example of that is POSIX threads, P threads. Okay, if we have time, I've got a small P-threads program that I'll show you. Okay, POSIX threads, it's up to the programmer who uses the POSIX threads library. It's up to that programmer. She's the one that has to do the scheduling. Okay, she's the one that takes care of it.
So Dr. Morris, in your slides, it shows that most of the time when you was talking about threads, it was in the OS system. So
It's both ways. In the slide that you're thinking of, I show it both ways. And the question says, it's got the imperative, thread scheduling must be handled. If that was not the imperative, if it was made, then the answer would be true.
Yeah.
But since it's the imperative, must or shall, it's not true. Next question, I think everybody got this right. Fork and exec is the only way that the operating system can create a new process after it boots. In particular, the shell does that. Combination of fork and exec. And we did that not only in class, but a homework, where you built a little mini shell and then you ran some watered down versions of operating system shell commands. The next one, all child processes created by a given parent have the same process ID. Of course, that's bunk. No, if it's a child process, it gets a new PID. Now, in contrast, in the last one, all threads belong to the same process. That's the difference between a process and a thread. And the reason a thread is called a lightweight process. All threads belong to the parent process. Therefore, they all have the same PID. All right. The next one, question number 4, was just straight out of the slide. The three states are running, blocked, and ready. Okay. And then some of you either only showed the states and didn't discuss the transitions. Some of you only showed the transitions and didn't discuss the states. I wanted both. A state transition diagram, you have to talk about the meaning of the state, and you have to talk about the meaning of the transitions. The state are the bubbles, the transitions are the arcs that connect them. So you need to talk about both. You can look that up in a slide. It's pretty easy. Okay, question 5, which of the following can lead to starvation? We know first come, first serve can't, because if I show up, eventually my job will finish, and then the next person. So, shortest job first can lead to starvation. All right? Round robin, no. Eventually everybody gets a chance. So round robin can't lead to starvation. Priority can lead to starvation. Then the second part B is why. So shortest job first, an endless stream of short jobs will starve long jobs. And then for priority, an endless stream of high priority jobs will starve lower priority jobs. All right? The word that I wanted in part C was called promotion. Okay, promotion. And there are a number of words you can use. Kristen used the terminology aging. That's a form of promotion. Okay? So essentially, the general solution is you promote. Now, for the 2 cases that we looked at, and in this case of the shortest job first, every time a long job is bypassed, you shorten its estimated runtime, or conversely, okay, you keep lengthening the estimated runtime of short jobs. Sometimes you do both. Okay?
You know, when I was reading that, I was wondering, but how would that affect the actual?
The actual runtime?
Yeah, how would that affect the actual person that's waiting for this job? He's waiting.
Yeah, so yeah, it's a different story. So yeah, we run into this all the time at work. The data center guy, he's interested in throughput. Okay, the person that's waiting for their job to run, they're interested in response now. So if I've got a really long job, we have guys that wait in the queue 3, 4, 5 weeks so that they can get 10,000 cores so that they can run their job. You know? So yeah, it's a tough problem. It's a tough problem.
One of them papers talk about that too, don't they?
Yes. All right, so shortest job first, the way you do promotion is you shorten the estimated runtime of long jobs. And eventually, even though it will run longer than what you said, what the estimate says, the scheduler will think that it's a short job, and it'll run it. Okay? Then, priority scheduling, well, every time a low priority job is bypassed, you increase its priority. Now, both of these can lead to some problems. Okay, both of these, particularly the priority one. You know, if I've got some super low priority job, okay, and the system is running with a bunch of super high priority jobs, you know, like the airplane's getting ready to crash, you know, the houses are getting really big, really fast. That's a high priority job, okay, versus, oh, the seatbelt light isn't working, right? Oh, I never get to tell people the seatbelt light's not working. So this can lead to a scenario that's dangerous, okay, so you have to be careful.
Can you give an example of a super low priority job in terms of computing?
Not really. It depends on, it's too general a question. It's too general a question. I can give you an example of a high priority job. High priority process is someone hits the keyboard and moves the mouse. You want the operating system now. Because there's nothing worse than you move the mouse and nothing happens.
Yeah.
And it's like, fall out to lead or throw it against the wall. Okay, so. Okay, so promotion. Oops. The next question. I'm going to do this in general, okay, because I have people that still didn't quite get this. So you can take notes on this if you like. Suppose I have up here an inode, right? Now what does an inode have in it? Does everybody
Size.
remember? It's got metadata and then addresses, all right? So let's suppose that the inode, here's the metadata up here, and let's suppose that we have J direct address blocks. Okay, in the midterm, J was 10. All right? So, how many direct blocks can I point to from here? J of them. And then, suppose in addition to that, I've got a single indirect, a double indirect, and a triple indirect address. I'll explain how those work momentarily. All right? So, how many blocks can J addresses point to? J. All right, now suppose that each data block, suppose that a data block holds M kilobytes. All right? M kilobytes, whatever that happens to be. All right, it holds M kilobytes. With the single or the direct, okay, with the direct blocks, how much data can I reference? Isn't it J times M? Right? Because what do each of these addresses do? Each of these point to M kilobytes. You see it? This guy points to M kilobytes. Da, 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 da. This guy points to M kilobytes. So it's J times M. Makes sense, right? J times M kilobytes. Now, let's suppose that this data block, there's two purposes for a data block. The first purpose is when it holds data. The second purpose is when it holds addresses, because it serves as an indirect, either double indirect, single indirect, double indirect, doesn't matter, it's an indirect. So let's suppose that when it's a data block, it holds M kilobytes. But when it's an indirect block, let's suppose that it handles P addresses. It holds P addresses. All right? So then, here we go. So do we have the scenario straight?
Times
All right.
times P times M.
So let's try it. So if I only use the direct blocks, the direct addresses, we know that we get size of the direct. Let's say the size, I'll just call it 1. Size 1 is what? J times M kilobytes. All right? Suppose that I'm using the direct plus a single indirect. So not only do I have the JM blocks here, what happens to the single indirect? What does he point to?
M.
Another.
So P.
He points to a block that contains P addresses. Agreed? Now each of those P addresses, what do? They point to M kilobytes. You see it? Like this. M kilobytes. So how much is here?
P times K.
It's P times M.
M, yeah.
Right? And then how many is here?
J times M.
J times M. So it's going to be M times J plus P, isn't it? Do you see it? In one of the earlier exams that I gave, M was 1. Okay? M was 1, and so I got answers this time that were based on a previous midterm, which I thought was a little humorous. That's why I'm taking the time to go through this more carefully.
Doc, I have a question. Now, in
Yes.
terms of physical memory, there is no difference in the data block or the indirect block.
It's
right?
just a chunk of disk space.
Correct.
It doesn't matter. It's the way it's being used. Now, so this is how much it would hold if I used direct plus single indirect. What if I used direct plus single indirect plus double indirect? Let's take the double indirect. So what does it point to? It points to a block of how many addresses?
M.
P.
P.
It points to P addresses. Now, what do each of those addresses point to?
M.
No, it points to P addresses. Yes? And then that in turn points to M blocks.
Okay.
M bytes, M kilobytes, like that. Right? And so then, how many kilobytes do I hold from this one?
P.
J to M.
PM, right? How about this one that's here? PM. How about this one that's here? PM. All the way down to PM.
Yes, many PM has a number of P.
Now, how many of these are there?
P.
There's P of them, right? So this guy is what? This is going to be M times J plus P. That was the direct plus the single indirect,
Okay.
right? And watch, plus P squared, right? Because it's P times P, then times M. And plus P times M, plus J times M, right? Now, one more time, okay? We take this guy out, okay? He points to how many addresses?
P.
P of them. Each of those points to how many addresses?
P.
P of them. Each of those points to how many addresses?
P.
P of them, and each of those in turn finally points to
M.
M. You see it? So, how many of these are there? How many data blocks? How many kilobytes? PM. How many's here? PM, 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 PM. So this one holds P squared M, right? But how many does this one hold?
PQ of M.
P squared M. How many times does this one hold? P squared M. P squared. And altogether, how many of them are there?
P
P of
squared.
them. So what's P times P squared?
P.
is P cubed M, right? So therefore you get the maximum is, well, M times J plus P squared plus
P cubed.
See
Okay.
it?
Yes.
All right? So, what if I had quadruple indirect? Then it would be P to the fourth. In the way this is structured, right? Maybe I'll change it, right? So you have to be able to reason. You need to understand not only this specific example, but the whole idea, the whole concept. Does that make sense? Right. Good. So that was the question dealing with version 7 of Unix and its file system. I think so. The question 7 had to do with the requirements for deadlock. And remember, there were 4 conditions: mutual exclusion, hold and wait, no preemption, and circular wait. Mutual exclusion said a resource can't be used by more than one process at a time. This is a mutually exclusive resource. Only I can use this. I can't use it and you use it at the same time. This room isn't a mutually exclusive because multiple people can use it at the same time. All right? So what's hold and wait? That means a process that already has some resource can hold that resource and wait for another one to become available. Okay? In other words, you can allocate resources on the fly as you need them. Okay? No preemption says you can't be forcibly, a resource can't be forcibly taken away from you. And then finally, the circular wait says 2 or more, and it's important to include the circular chain business. 2 or more processes form a circular chain where each of them is holding a resource that somebody else needs. Okay? Everybody's holding a resource that somebody else needs. Okay? How are we doing on time?
16.
Oh, okay, good. Okay, so number 8, the 2 processes. So remember the way P works. How does the P semaphore? How does the C portion of a semaphore work?
It increases by 1.
It decreases it by 1.
1. Okay.
And if the subsequent semaphore is
Non-negative.
It's not negative.
it's non-negative. If the result is non-negative, then the process that invoked P can enter the critical section. All right. So that's the way P works. All right. What if it's negative? Then what happens?
It knocks off it goes on the waiting list.
Yes. Then it goes. So there's 2 cases. Either no matter what, it decrements it. The Dutch word is probeer. That means to probe or to test. Okay, probeer. It's Dutch, probeer. So you test it, you decrement it, and then if it's non-negative, you go into your critical section. If it's negative, you go on a waiting list. All right? So that's what P does. By the way, the P has already been executed. A common mistake is for people to then go back and re-execute the P when they come off the waiting list. And then you end up decrementing the mutex twice. No, it only decrements it once. And it's below the mutex, and it's on the waiting list. As soon as it comes off the waiting list, it's in its critical section. So you don't do the P twice. So, how about V? What does V do?
V increases by 1.
Increments it, and the result says what?
If it's
non-positive, then it pulls something off the waiting list. Okay? And proceeds. All right? So one other process invokes a V. The increments his mutex, and then the operating system, whoever the mutex handler is, then looks on the waiting list for someone else to run. All right? If there's no one else to run, then just do that. So then, with these ideas, let's see. A, what is the value of M just before and just after P1 invokes P? Well, before it's a 1, after it's a 0. B, what happens to the process after it invokes its P? Well, P, by the way, as I said, explain. A lot of people just gave an answer with no explanation, okay? And so I banged you a point on that.
Yeah, you did.
Yeah, you did.
Okay? And I was giddy. It felt so good.
I bet it did.
Painful. Painful.
So, M is non-negative. Therefore, process P1 enters the critical section. C, after P2 executes its P, okay, excuse